You throw a ball off a roof of a 9-meter tall building. Your target is a bullseye that is 2/3 of the way up a 15-meter tall tree, which is 30 meters away from the base of the building. Assuming you are 1.3 meters tall and you throw at an angle of 45, or you throw at a 45-degree angle, how fast must the initial speed of the ball be to hit the target? So if IDESA required, we're going to use our 6-step problem-solving method for this. This is a really good example of projectile motion. So my F, or find, for FIDESA, what is it that I'm looking for with respect to the variable or the letter it looks like in an equation? The initial speed of the ball is going to be my initial velocity. So V initial, that's the thing I'm looking for. An image, let's kind of draw out what's going on with this. So the building we're saying is 9 meters tall. It's not going to be fully to scale, but just so we can kind of get an idea of what's happening. We are 1.3 meters. The ball's leaving our hand at approximately our height. That does not look like a 45-degree angle. This is the initial velocity. That would be the 45-degree angle the ball leaves. It hits 2/3 of the way up a tree that is 30 meters away. So we're going to say this is a tree. I'm so good at drawing trees. And this is 30 meters away. Here's the target, which would be 2/3 of the way up. Something like that. And the entire tree, again, not perfectly to scale, but the entire tree would be 15 meters. So that's kind of an image of what's going on. I know the ball's going to arc in a parabola. So this is two-dimensional kinematic equation. D for data. What are the numbers that I'm given or things I can infer? I can know my initial height that the ball leaves. Y initial, that's going to be the 9 meters plus the 1.3 meters. That's 10.3 meters. The final height of the ball is, I know that one as well, even though it's given to me in a bit of an abstract way. It's 2/3 of 15 meters, which is 10 meters. I know the overall horizontal distance the ball travels. That's just going to be 30 meters. And I know the initial height, or not the initial height, I know the angle, the initial angle that the ball leaves. It's going to be 45 degrees. And that's about all the things I know. I know it's going to stop, but that doesn't really help me in terms of calculation. So we can pretty much be done there. The equations involved, so the way I would set this up is remembering the whole purpose or the point of trying to do FIDESA is to link these variables and the variable I'm looking for and which equations overlap those things. And there are two that I'm thinking of in terms of kinematics. I'm thinking of x final equals x initial plus v initial t plus 1/2 a t squared. You might say we don't know a, but if I make this vertical, we know gravity is the acceleration in the vertical direction. So, and then I know the velocity is considered or defined as the change in position over the change in time. So those are the two equations we're going to be using. And we don't need any more. I know that because I wrote this problem, but you could write down a few more if you thought you needed them or add them later. The solution set. So here I'm going to start with transferring my equations into the specifics of what we're working with. So instead of writing x final equals x initial, I'm going to put it into the vertical direction, the vertical perspective. So y final equals y initial plus, this is now just the vertical component of the velocity, v I y t. And then I'm going to have this be minus, because gravity I'm going to define as negative g instead of negative 9.81. Now, where you define it's up to you, but we need to account that gravity is going to be pulling it down. So I need to account for that direction somewhere. The way I prefer to do it is by writing negative 1/2 g t squared. Okay, this is better, looking a bit better. I already know y final, y initial. I have a relationship for the initial velocity, but that's also the thing I'm looking for. I know gravity. I don't know time. So we need another equation in there. But you'll notice the amount of time it takes for the ball to travel horizontally is going to be the same time it takes for it to move vertically. And after the ball leaves my hand, its horizontal velocity is constant. There's no acceleration in the horizontal direction. So it's going to just travel at constant speed. So that's going to be the tie over and how I calculate my time. So the velocity initial in the x direction is equal to the horizontal displacement over time. And then I know two other things. I know that the way I obtain the vertical velocity component is by taking the whole velocity and multiplying it by the sine of the angle. And the same thing for the horizontal. So initial x is going to be the whole velocity multiplied by the cosine of the angle. And these are going to be what I'm going to use to solve this. So let's rewrite a few things. Here, I'm going to rewrite my time equation first. So I'm going to swap. We know our algebraic manipulation. These two things can change places. I'm also going to rewrite the x component of velocity as the cosine times the whole velocity. So that's going to look like time is equal to the change in x, the displacement distance, over the whole velocity times the cosine of the angle. So that's what time is. And anywhere in this initial equation, I'm going to replace t with that expression right there, just a straight up substitution. I'm also going to replace VIY with this expression right here. So that's going to give me y final equals y initial plus this becomes, oh, that should be a v, vy sine theta. Instead of writing t, I'm going to write delta x over vy cosine theta minus 1/2. This is g. Pay attention, this is squared. Delta x over vy cosine, yep, cosine theta. All of that is squared. And that's a mess, but there's ways we can simplify it. So something you'll notice, the vy's in the first term at least cancel, and then sine over cosine is defined as tangent. That's a trig identity. So I can simplify that, and I'm going to distribute the square to get rid of the square root. So I'm also going to move the vi to the other side. So v final minus, or y final, sorry, minus y initial is equal to delta x. This then becomes tangent theta minus, this will be, I'll write g over 2 delta x squared over vy squared cosine squared theta. So that looks a little messy, but we'll hopefully simplify it a little further. So that turns into that. Now, my goal is to isolate vy, get it all by itself. So I have to undo things, think back to our order of operations. I'm going to subtract this to the other side. So I get y final minus y initial minus delta x tangent theta is equal to negative g over 2 delta x squared over vy squared cosine squared theta. I could do this all in one step, or you can do them at separate steps. But again, I am just undoing things here. I want to undo the divide by 2, so I would multiply. I want to undo the multiply by negative g, so I would divide. And I could do the same thing for the delta x squared and the cosine, leaving just vy by itself. So essentially what that's going to give me is I'm going to have 1 over vy squared as equal to, I'm going to kind of copy paste this here because this is all, you have to be careful about how we distribute this. So this is all in parentheses. And then on this side, I'm going to have negative 2. This is going to be cosine squared theta over g delta x squared. Now you'll notice this is in the denominator. We don't want it in the denominator. If I take the reciprocal of everything, it checks. But honestly, what I could do is I could just take the or square root of all of this. However you do it, that's kind of up to you. I'm going to scroll down a little bit, running out of room. I get Vy as equal to delta x over cosine theta. And then all under this square root, I essentially have, you can kind of write it like this. This is going to be g and then all over 2y final minus y initial minus delta x tangent theta. Gets a little messy, but how you write this is kind of up to you. Did I have to put it in a square root? No. Could I have also written it to the -1/2? Yes. But that's kind of up to you on how you do that. And then that's it. That's my answer. I'm going to plug in my numbers and check my results under A, the last part of our acronym answer. So A, our answer, our delta x, the vertical or the horizontal distance or displacement was 30 meters. This is divided by the cosine of 45 degrees, which is unitless, all under the square root of, this would be 9.81 meters per second squared over 2, which is unitless. Our final distance was 10 meters minus the 10.3 meters minus the 30 meters times the tangent of 45. This is under my square root. My meter unit is going to cancel with the numerator and the denominator, leaving me seconds squared in a denominator. Under square root, that's just going to give me seconds. I have meters out front divided by seconds, which is the unit for velocity. So it looks like we set this up correctly. If I plug into my calculator, I get 17.07 meters per second.